Hi, I'm Jacob Story and I'm going to be taking you through my technology manual for my project, Moulding for the Masses. Over the duration of the project, I investigated several different technologies, including various metalworking techniques, optimal temperatures and materials for injection moulding into 3D printed moulds, and the electrical specifics of the heating components involved. I then applied this knowledge I'd gained to my project. The project Moulding for the Masses was centred around an open source hand-built injection moulder that would use 3D printed moulds. As it was necessary for my product to comfortably and repeatedly reach temperatures of around 200 degrees Celsius and conduct this heat from its outer surface to its inside, it had to be made from metal. Previous to this project, I had no prior knowledge or experience of metalwork. This project was also made to be open source, so I had the goal of not only being able to create my product, but becoming competent enough in the metalwork techniques that I'd feel confident in writing instructions for others to repeat the process. I knew the dimensions of the product I wanted to construct and how it would mechanically function, so I made a CAD model of it on SolidWorks to act as a guide. The ram, nozzle and base of my product were made from solid steel. The machines used to shape these pieces were a metal lathe and metal mill. I learned that when using these machines to remove material from solid metal, it's essential to perform incremental passes of around 2 millimeters. If you attempt to cut away any more than this, you risk damaging the cutting tool of the machine or shearing the part you are working on. To ensure you incrementally increase these passing cuts accurately, I learned you must first use the control panel of each machine to zero the cutting tool in relation to the part you are working with. On both machines, you move the part in relation to the cutting blade using X, Y and Z axis wheels until the cutting blade intersects the part. You then set the value to 0 on the control panel for the respective axis you are moving the part in. The remaining parts of the frame of my injection moulder were cut on either a bandsaw or a chop saw. The next step was welding these parts together. Again, I had no experience with this process bar an induction 5 years ago, so I had to be re-inducted by one of my university's welding technicians. He advised me about technical specifics such as the recommended voltage and wire speed values for the materials I was working with. I then performed a couple of practice runs on some scrap metal. My first attempt at welding could have been more aesthetically pleasing, but as my product's functionality is much more fundamental than its appearance, this was not a huge problem. I was taught about the speed and distance the welding torch should be from the part to ensure adequate weld penetration that would produce strong joints. I was also taught after my first round of welding that my welds would be much more aesthetically pleasing if I beveled the edges of the parts I wanted to weld, so I made sure to do this for all my subsequent flat welds and yielded good results. As this type of heavy machinery work requires learning to be done under the supervision of a qualified professional for health and safety reasons, the primary accreditation of my learning are the credentials of my university's metalwork technicians. The largest technical difficulty faced throughout the project was experimenting with different 3D printed materials for the mould and finding the correct temperature for the moulder that would result in a repeatable process that produced good quality parts. I experimented with different combinations of ABS, PETG, PLA and resin for the mould material, PLA, ABS and polymorph pellets for the injected polymer, and temperatures ranging between 160 and 200 degrees for the injection temperature on a C.R. Clarke injection moulder. This experimentation took 6 iterations to achieve a successful injection. The main problem I faced was extracting the injected part from the 3D printed mould once it had set. I first assumed this must be because the injection temperature was melting the mould surface, fusing the injected polymer and the mould together. So I looked up further temperature properties of the materials I was experimenting with and learned about the glass transition temperature for the polymer pellets I was injecting, which is the lowest temperature at which materials become malleable. This was relevant as I wanted to attempt to create the largest temperature gap possible between the injected polymer and the mould to try and prevent the mould from melting. However, I later concluded that the low melting point polymer polymorph pellets actually had adhesive properties that were essentially gluing the moulds together. I attempted my next iteration with PLA pellets and yielded much better results as I could now consistently separate the two halves of the mould after injecting. I still faced problems ejecting the part from the mould however, but determined this to be due to the mould design. I next redesigned the mould to have holes for extraction, but this ended up breaking the injected part as the PLA pellets produced a relatively brittle part material. Finally, I redesigned the moulds to have a split design in the hopes that the ejected part would simply fall out when they were pulled apart. This process produced my first successful injection. The other main technical challenge was figuring out the electronics needed to heat the barrel of the injection moulder. My goal was to learn the basic electronics behind heating elements to enable me to safely and repeatedly heat up the barrel of my product to around 200 degrees Celsius. I had several face-to-face in-depth chats to a university electrical technician about both the electrical specifics of the heating system and the health and safety risk factors this may present. He advised me about the problems with some of the electronic components I'd purchased for the project. The main being that the band heater and SSR controller had incomplete datasheets. This meant that the current rating for the band heater was unknown, meaning it was also unknown how much current would be passing into the SSR controller. This was a problem as the resistance value for the SSR was also missing, so there would be an unknown degree per watt rise in temperature when it was switched on. This in turn could cause a runaway system where the components would heat up exponentially until they failed, potentially very dangerously. In hindsight, I should not have purchased cheap non-CE marked components to attempt to save money. I rectified this problem by purchasing a bimetallic thermostat from a well-established UK supplier. Thank you very much for listening.